Hello and welcome to our online discussion of the quantum mechanical model leading into directions on how to complete electron configurations. Up to this point, we've been really working heavily in the Bohr model of the atom, emphasizing those energy levels and using those rings to indicate where those energy levels are. However, that's still not quite as accurate as it could be for our current model of the atom. The biggest difference is that we really can't tell an exact location of an electron. We have probability, we know roughly where it is, and we know where they are more likely to exist, but I can't say that like electron 5 in oxygen can be found in energy level 3. We know simply that they exist in certain regions. So this probability cloud that you see over here is showing more dots in the locations where electrons are more likely to exist. So our understanding is that there are specific regions where the energies of the electrons make them more likely to be. We can give probabilities of finding electrons in a region, but we cannot tell exactly where it is at any given time. Now, within the atom, we've been talking about these energy levels, and there are 7 within an atom. The first energy level, when we learned the Bohr model, we saw that there were 2, and there were 8 in the second energy level. Now, one of the biggest differences here and why the Bohr model did not work is the third energy level could actually hold 18. And by the end of this discussion, we're going to see where those extra regions are that allow it to hold more electrons than what we thought it could. And it's going to have a lot to do with those transition elements on the periodic table. The fourth energy level can hold 32. So what we see is that the more energy in the level, the more space for electrons there are. The higher the energy level, the further it is from the nucleus, and the greater the energy of the electrons that are in that region. So think of them as having to overcome that attraction between the nucleus and those electrons. In order to overcome that attraction, they have to have more energy to disrupt that force. Now, the energy level part of this diagram is where we're going to be able to make the best connections to our analogy. When we take a look at the sublevels, these are areas within an energy level. Think about our analogy of the boarding house. This would be like the rooms. So the rooms would be those different types of areas within the energy level that had certain amounts of electrons that they could hold. Each of the sublevels have different energy values, which in the POGL, remember we represented with the offsetting of the boxes within the level. The orbitals are these regions where we have sections. So there are S, P, D, and F orbitals. We've already been introduced to the S and the P. We'll be talking a little bit more about D and F today. The maximum amount of electrons that we can hold is 2. This is just like the bunk bed having 2 borders in it. So within a sublevel, you can have 1 or more orbitals, and each orbital can hold 2 electrons. So when we take a look at this diagram, we are able to see that for each sublevel, there's a certain number of orbitals that holds a certain number of electrons. So think of sublevel S like the sunny room. There was 1 bunk bed that could hold 2 electrons. The P sublevel was like the pink room. The orbitals are like the beds themselves, the bunk beds that can each hold 2 electrons. Now the D sublevel has 5 bunk beds in it, so this would be an even bigger range, a bigger space to hold even more electrons, and this will build and get larger as we go. But the pattern is the sublevel will have a certain number of orbitals and types of orbitals, and that's going to determine how many electrons we can hold. One quick check, if you take a look at this chart after you fill it in. One of the things that I need you to do is to complete a summary of how these parts connect to the boarding house. So in the right-hand column, next to the table, this is something I will be checking for to make sure that you've completed. This helps me know that you are listening to the words and making sure to check in. So write a 1 to 2 sentence summary about the boarding house and how the orbitals and sublevels are connected. Now, not every energy level has the same number of sublevels and therefore orbitals. This does help us connect to the Bohr model. When we think about the first energy level, it only has an s sublevel, which we said has one orbital that can hold 2 electrons. That's why when we drew the Bohr model, say for helium, we could only have 2 electrons. That limit of 2 is coming from the fact that there are only 2 electrons in that first energy level because it only has an s sublevel. Now the second energy level has an S and a P sublevel, just like the second level of the house and the boarding house. So it can hold 2 in its S orbital, or bunk beds, and 6 in the P. 2 plus 6 is 8. That is where the 8 is coming from in our second energy level. Now in the third energy level, in addition to having an S, a P, it also has a D sublevel, which we just learned can hold up to 5 orbitals and therefore 10 electrons. Well, 2 from the S, 6 from the P, and 10 from the D will give us 18 total electrons. All of this is represented in the periodic table. So you'll see that the regions of the energy levels are represented colored on the periodic table on the right. We have S sublevels in the yellow, so notice the first 2 columns. We're really talking about where the valence electrons end up. D sublevels are blue. The pink shows where we have P sublevels, and the F sublevels are with those inner transition metals down at the bottom. We have to have big enough elements to have space for those electrons to go. Now remember we talked about these having kind of a cloud or a high probability area around the nucleus where they're likely to be. An s orbital is simply a sphere. So in a sphere that is a defined distance from the nucleus, the electrons tend to spend most of their time. Now with the p orbitals, it's kind of like a dumbbell shape or the outline of a figure 8 that's filled in. When you look at those 3, they overlap around the center point. So I'm going to draw them in kind of like on that 3-dimensional scale so we can see somewhat how they would look when they're all together over the same spot. So they all intersect that main point, and then the electrons within that p sublevel could move anywhere within that section. A p sublevel is a higher energy than an s sublevel. Now, I'm not going to ask you to remember the shapes of the Ds because they get a lot more complex. It's kind of like a clover shape, and just like they overlapped on the 3-dimensional axes up here, the same would happen for those down below. So we have our spheres here. Notice that as the energy level increases, so does the volume of that probability cloud. So what's happening is the further we get from the nucleus, the more energy it takes to get there, meaning there's more locations where those electrons can be. Again, the p orbitals have that 3D kind of dumbbell shape, and they would intersect at that middle point on all 3 axes. The D and the F orbitals I would not ask you to remember for a test or quiz. Now, we always start going from lowest energy first and then filling into higher energy. This is the more stable state for elements. This is not a rule that we make. This is an observation we make from our data when we observe elements. So the blue sphere in the middle is our 1s. We would see that we would then move into the 2s, which is the kind of green overlapping sphere. From there, we would go into the 2p orbitals, and then the 3s would be filled next. So you'll notice that each one, every time I move to a higher energy level, that section completely fills and overlaps and is outside the region of the one before it. Now, an electron configuration is what we talked about in class, is simply being an address for the electrons. Where do they exist? And there are three principles that we follow when we record and write down where they are. These are the observations that we see in real atoms. The Aufbau principle says that we always fill the lowest energy orbitals first and then work our way out to highest energy. So it's what we've been doing, but now we have a name for it. The Pauli exclusion principle tells us there's a maximum of 2 electrons in each orbital. So when you think about your diagrams in the POGL, those arrows that had the upside down spins, think yin and yang, I always have to pair up the opposites. That's how you can get these negative things next to each other and to be relatively stable. Lastly, Hund's rule, the one that we really can't see until we get to our orbital diagrams, is each same spin electron must fill an empty orbital of equal energy before doubling. This was like the manager's rule, where you had to have one person on the bottom bunk before you could put people on the top bunk. So the format again, the large number out in front is the energy level. The letter is the sublevel, which means I can only ever have S, P, D, or F. And that superscript is the number of electrons that are present. Now, all of our work is going to come back to the periodic table. We're going to be tracking through the periods. What you'll notice is that each period represents an energy level. So when we look at the elements in their rows, this is one of the biggest things that helps us understand why the valence electrons are the same in each column. If I'm simply adding an electron for every proton I add into the nucleus, I'm moving myself right across the rows. So the first step is I'm going to locate the element on the periodic table that I want to write the configuration for, my address of the electrons. I'll fill the orbitals in as I move from hydrogen across to that point, and then make sure the total number of electrons that I want to place are equal to the atomic number for a neutral atom. So these examples are listed in your note sheet, and I'm going to go back to the periodic table slide so that I can do a few. You want to put them into your right-hand column. Now for C, carbon, that's located at the top of column 4A, which is right here. So also, because its atomic number is 6, I know I need to place 6 electrons. So what I'm going to do is start at 1s, that's the hydrogen atom, and start placing all of the electrons as I go, making sure I keep track of my rules of how many electrons fit, and writing down all of the information of where they are. So I'm going to start at 1s. And I see that on my way to placing 6 electrons, I cross 2 of them in the 1s energy level and sublevel. When I hit the end of a row, I'm going to move on to the next one. So I go to 2s. I pass 2 electrons in the 2s region, but I have not gotten to 6 yet, so I move on to the next portion of the row. And what I find when I reach carbon on the periodic table, it took 2 positions to get there, which means there were 2 more electrons. Now, when I add up the electrons at the top, I'll see that I have 6 total electrons, which is the number of electrons I needed to place for carbon. We're going to move on and represent that in an orbital diagram and some shorthand notation, and we'll have another opportunity for additional practice later. Now, sometimes these could get really long. If you notice that I had to move all the way across the periodic table, all the way through all of the rows, that might become very challenging. Okay, so when I take a look at one like chlorine, we'll go back and do that in the shorthand. I'm going to use the noble gas, and what I'll do is write out the chlorine one for us so we can see how it's different. Now this one would be a little bit longer, and you'll notice that the 3D does come before the, or come after the 4S. What I'm going to do is find the element at the end of the 3P column, which is argon. And simply write the rest of the information from that point. to get there, if you take a look, to place those 26 electrons, I simply all the way went from hydrogen